Hi, we are from course SEE 523, Section 3, Group 1. In this video, we will present on the topic of displacement current. Before we slap into the topic, I would like to introduce our group member, Akhilesh, Wei Jiahong, Lim Jiayu, K Kai Wei, and me, Chong Zhishen. First of all, I would like to introduce the concept of displacement current. Displacement current is a concept that describes the flow of electric flux in a region of space, even in the absence of conventional electric current flow or the movement of charge carriers such as electrons. Displacement current occurs when an electric field changes in the medium, resulting in the formation of corresponding magnetic field. Or in other words, displacement current introduces that a time-varying electric field without the physical movement of electric charges will produce a magnetic field similar to a conventional electric current flow.
In the next part, we are going to learn and understand the Maxwell's equation related to displacement current in electromagnetics. Maxwell's equation stands as the cornerstone of electromagnetism, encapsulating its fundamental principles. Within these equations lies a critical concept called displacement current. Introduced by James Clerk Maxwell to extend Ampere's law, displacement current serves to fortify the consistency of Maxwell's equations, particularly in accommodating changing electric fields within a region. This addition proves essential as it enables a comprehensive description of electromagnetic phenomena, accounting for dynamic electrical environments. Without this augmentation, the equations would falter in capturing the intricacies of time-varying electric fields. Through Maxwell's foresight and innovation, the realm of electromagnetism expanded, paving the way for deeper insights into the behavior of electric and magnetic fields. Now let us start deriving the Maxwell's equation. We know that from the continuity current equation, the curl of current density is equal to the negative partial derivative of charge density with respect to time. Before this, we concluded that the current density vector is a curl of the static magnetic field vector. Therefore, we substitute it into the continuity current equation. According to vector identity, we know that the divergence of the curl of any vector will always be zero. Therefore, the whole equation now is also equal to zero. To overcome this drawback, we add a general vector to the static field equation. Then, the right-hand side is basically equal to the curl of the current density and the curl of the displacement current density. Then, we cancel out the curls of the left-hand side and the right-hand side, which leads to the final form of the Maxwell's equation, states that the curl of the static magnetic field is equal to the conduction current density, J, and the displacement current density, JD. So what is the role of displacement current density in the magnetic wave propagation? Actually, without displacement current JD, the propagation of magnetic waves would be impossible. This current is essential for the generation and propagation of electromagnetic waves. As for its frequency dependency, at low frequencies, displacement current is often ignored compared to conduction current. However, at higher frequency, especially in the context of electromagnetic wave propagation, the contribution of displacement current becomes significant. Now let's look at the historical context of this equation. During Maxwell's time, high-frequency sources were not available, and the equations couldn't be fully verified until Heinrich Hertz discovered radio waves. This highlights the historical significance of displacement current in the development and verification of electromagnetic theory. Also, the inclusion of displacement current in Maxwell's equation is essential in ensuring their consistency and accuracy. particularly in describing the behavior of electromagnetic fields in situations involving time-varying electric fields.
Now we are going to the equation of displacement current from its density, where I equal to integration of del D del T and del S. S is the area of the capacitor plate as shown at the figure at right side, and I is the displacement current. JD is the displacement current density where JD equal to del D over del T. And D is related to the electric field E as D equal to epsilon naught E. And the epsilon naught is the permittivity of the medium in between the plates. Now we are going to some of the relationship of Maxwell displacement current regarding to the capacitor plates as shown in the figure of the left side of the slide. So the uniform electric field between the capacitor plate will result in the Q over epsilon naught flux through the surface. And also the changing charge on plates will lead to the current term I equal to epsilon naught dq over dt to calculate the current for consistency. So because of the addition of this epsilon naught dq over dt, it will maintain the consistency in the Ampere's law, creating generalized Ampere's law. So well, the same goes with the magnetic field. The magnetic field magnetic will remain constant inside and outside the place due to this addition. And now we're going to the difference between conduction and displacement current, where conduction current is from charge flow in conductors, and the displacement current epsilon naught dq over dt is actually from the changing electric field.
So let's look at the application of displacement current. So one of the application of displacement current is the capacitor. So first let's have a look at a basic circuit consisting of a capacitor, a voltage source, and also two meters here. These meters are placed here to indicate the direction of current. So as soon as the circuit is connected, we can see that the positive charge will be flowing in this direction, which is indicated by the red line, and it will accumulate at this plate of the capacitor. And the negative charge, on the other hand, it will accumulate at this part of the capacitor. So if we look at the zoomed visual of this capacitor, this is the diagram that we can notice. The positive charge is accumulated at this end of the capacitor, while the negative charge is accumulated here. So what will happen when this happens? It will create an electric field line across the capacitor. So next, we look at the macroscopic view inside the capacitor. This means that we have to take a look at the atomic structure inside the capacitor. So we know that inside the capacitor, we will place dielectric of value epsilon, and it consists of molecules and atoms. So when the circuit is not connected, let's say we have a switch and it is open and the circuit is not connected. So the molecules and atoms inside the capacitor will be stationary, will stay this way. So as soon as the switch is closed, the capacitor will begin to be charged, and as stated before, the positive charge will start to accumulate here, while the negative charge starts to accumulate here. And this will create the electric field lines across the capacitor. As a result, it will cause the electron clouds of the atomic structure to move towards the positive charge. This is called a distortion or movement of electron clouds. So in a way, the distortion or movement of electron clouds towards the positive end of this capacitor is also can be seen as a movement of current, and that is why it is called a displacement current. So it does meet the basic concept of flowing of current Even without a medium or a physical structure inside the capacitor, even if it's empty, there is still a phenomenon that is similar to a current flow. So the expression for displacement current density, as we already know, it is just the rate of change of electric flux vector. So this is the equation that indicates the flow of displacement current density.
So, hi, Dr. Hanif. So, this is about our conclusion. So, firstly, the first picture is about the Maxwell equation. So, the first term is about the conduction current, and the second term is about the displacement current. So the right figure is about our experiment that to measure and observe the displacement current. So this is an this is a capacitor and it got the supply to the capacitor, and then the current go to the plate, and then it got the voltage, and then the charge will accumulate positive and negative at the both side. Okay, and then firstly, the definition about the displacement current is when the electric field change, displacement current exists. So secondly, is conduction current will go through the capacitor, and then we will observe and measure the different case of the current displacement. So the case one is about the magnetic field at R greater than capital R. So capital R is the radius of the capacitor plate. So if it greater than the capacitor plate and it is at the surrounding of the wires, it means that even though it go the line current, and then by the right hand rule, uh, the magnetic field will exist, but it's in the clockwise. Even though because the surrounding of the wire don't have the electric field equal to the zero, so the displacement current is equal to zero. So plug into the Maxwell equation, the first term will be left, but the displacement current will be zero. So same thing will go to the case two, because the is want to found about the point that the radius greater than the capital R, but in between above the plates. So same goes, the electric field equal to zero, so don't have the displacement current, just the conduction currents. So lastly is about the case 3. So case 3 is the magnetic field at the R smaller or equal to the radius of the plate, and it is in between the plate. Due to the electric field is not the zero, so it means that it is always changing over the time. So the plug the parameter into the Maxwell equation, you will find that the conduction current will plus the displacement current. So this is our project. So thank you, Dr. Hanif.